Okay, so let's first review what we learned from thermodynamics, which in a way physical chemistry a little bit. Okay, a very quick review. So the first thing that you learn in thermodynamics, let's just refresh our minds, not so much go into the mathematical detail, but from concept level. The first law of thermodynamics, what does that say? It's essentially the conservation of energy. We do not create energy from nowhere. Okay, energy can convert from one form to another form, from mechanical to heat, from heat back to mechanical, right? From mechanical to heat by friction, from heat to mechanical, that's thermal engine. Make sense? And then from electrical to mechanical, that's electrical motor. From mechanical back to electrical through electrical magnetic field, that's power generator. Make sense? It's all these types of energy conversion, but in this process, we said the energy got conserved. We don't create, it doesn't disappear. It's just one form to another form. Most cases from usable form, mechanical, electrical, to dissipative heat, which you cannot really use, especially low-grade heat. Make sense? That's our first law of thermodynamics. And then our second law of thermodynamics, it says, okay, quite often, there are many different ways to say it, but in a closed system, the system degree of randomness normally goes higher. The entropy term goes higher for so-called spontaneous process. Occasionally it goes back, but you have to put energy back into the system in order for the entropy to go lower. Otherwise, typically, the entropy would go higher. That's one way to state it. Another way, of course, there are other ways. Some other ways include, okay, normally from high temperature so-called heat reservoir to low temperature heat reservoir, that process would be what we call spontaneous. Without putting extra energy, the heat doesn't go automatically from low temperature reservoir to high temperature reservoir. You can do that. That's how heat pump work, but you have to put extra electricity into the system. For spontaneous process or for isolated system, then it normally goes like that. High temperature to low temperature. Make sense? High potential to low potential. That's first law and second law of thermodynamics. Second law, as we mentioned, enthalpy, which is another way to say heat, right? That's a measure of the system heat. Entropy, and as we mentioned, is a measure of degree of randomness, or another way to say a degree of order. High entropy means the system is more random, more scattered. Low entropy means the system is highly ordered, highly organized. That's very few configuration. That means low entropy. Make sense? That's what you learned. Okay, and basic free energy. Of course, there are different types of free energy that you define based on constant pressure, based on constant volume. One is called Gibbs free energy, the other one Helmholtz free energy. But typically, we are dealing with constant, in this word, constant pressure. In most cases, we are dealing with constant pressure. So when for physical process, for material aspect, we quite often are more concerned with so-called Gibbs free energy. G defined as H minus Ts. H is your enthalpy term, and T temperature, S is your entropy term. That's typical the Gibbs free energy term that we use more. And of course, there's the Maxwell relationship. Okay, review it yourself. I myself may not remember it. Okay, and then temperature and pressure effect. Okay, for process to happen, when you go to higher temperature, if the process is so-called endothermic, it absorbs heat, then at higher temperature it happens typically more faster because you're supplying the heat. It absorbs the heat. If you at higher temperature provide more heat, the process goes easier. Similarly for pressure, right? If the chemical reaction reduce the volume, the pressure happens, it would higher pressure would facilitate the process if the process is a reduction in volume. Okay, temperature and pressure effect. Equilibrium. Equilibrium means what? Well, means kind of same chemical potential, flat. Or the rate of going forward is the same as rate going backward. One example would be ice and water coexisting at if one atmosphere, ice and water coexisting at what temperature? 0 degrees C or 273 K, which means at that temperature, at under that pressure, 1 atmosphere, for that cube of ice, it can exist indefinitely as ice, or it can exist indefinitely as water, or I put ice and water together, I check back 1 day, for 1 year, the relative amount may not change. At any moment, there may be a little bit of ice going into liquid water, but equilibrium means at the same time there will be equal amount of what? Liquid water going back to solid ice. That's what equilibrium, which means you check back one day, it's roughly the same. Check back 1 year, it's roughly the same. Let me ask you this. At room temperature, can an ice exist for a little while? For a little while, yes, right? You open your refrigerator, take out a piece of ice, put it on table. At room temperature, does it exist? Well, at least it's a tricky question. You think the surface, the inside, probably inside of that ice is still cold. Outside, quickly that ice starts to melt, right? You check back 1 day, if that piece of ice is not too big, you check back 1 day, that ice become complete water. Even if I put it in a closed container, as long as the temperature is the same, I put that in a can or in plastic bottle to prevent evaporation, as long as the temperature is room temperature surrounding, eventually that solid ice, whether it's in a container or it's open, has to become liquid. So that is not equilibrium. Make sense? On the other hand, if I put that ice in my freezer, I put my ice in my freezer, I check back 1 day, that looks like solid ice. I check back 1 year, that looks like solid ice, as long as I don't lose my electricity so that I lost my temperature control. As long as I can control the temperature, that piece of ice doesn't really change. That is also equilibrium. Make sense? The ice is at equilibrium state if it is below 0 degrees C. Make sense? That's what we learned. And defects in solid, we said, okay, boy, we learned the crystals. In crystals, atoms are arranged in fashioned order. Okay? But we said, okay, because of the Gibbs free energy, there will always be at finite temperature, there will always be some defect in the system that create randomness, that increase the entropy term. As long as our temperature is not absolute 0, you will always have defect, no matter what. That's just the nature. That's where defects come from. Even though, okay, perfect crystal only exists ideally under ideal absolute 0K. And we never ever reach absolute 0K. Make sense? Defect in solid. And because of defect in solid, that leads to many other stuff. And we said, okay, are defects always undesirable? Well, sometimes defects by its name is undesirable, but sometimes, believe it or not, you have to have defects. Or it's beneficial, like semiconductor chip. Pure silicon versus silicon with some dopant, which one has defect? More defect. The one with more dopant, but it's through dopant that we have this p-n junction for semiconductor for all chips, right? If we only have ideal perfect crystal silicon, we don't have semiconductor, we don't have computer chips. We calculate by hand. Make sense? So, and then you in thermodynamics, you also learned the important concept of so-called solution. Solution for chemists, the first thing that comes to mind is a liquid solution of something, quite often in water, or some other so-called solute in solvent. But for material scientists or material engineer, quite often we are dealing with so-called solid solution because we are dealing with material, whether it's polymer or it's metal or ceramics. We are dealing with solid material. Materials engineer not too often deal with pure liquid gas. That's probably belong to the domain of either chemistry or chemical engineering. Material, we're dealing with quite often solid material. Solid material, solid solution, which means, okay, the stuff is solid, but there is some type of mixing like what is happening in liquid, except now everything is solid. Okay, and for solution, thermodynamics, we introduced the concept of so-called partial molar quantity for whatever so-called extensive quantity. Now temperature is so-called intensive quantity, or pressure, intensive quantity, but so-called extensive, which means the system quantity depends on how much you have. Volume is a representative of so-called extensive quantity. You have this much material, 1 kilo versus 2 kilo, they definitely typically have, for solid, different volume, right? The 2 kilo would have typically double the volume under the same pressure of that of 1 kilo for the same material. That's so-called extensive quantity. And partial molar quantity would be the quantity that divided by the molar, so that we get a intensive parameter. And one of them is so-called partial molar chemical potential, partial molar Gibbs free energy, which is our so-called chemical potential, mu term, chemical potential. And that is a very fundamental term that we use it, okay? Chemical potential, partial molar quantity. And then activity. Activity we learned in chemistry, we learned concentration. Within 100 gram of so-called solution, how many gram would be the solute? The remaining would be the solvent. That defines concentration. And but concentration, that's complexity. But we said, okay, under so-called dilute condition, the concentration would be equal to the so-called activity, which means how active that solute would be. Okay, activity. And then under dilute condition, the so-called activity coefficient among the so-called ideal solution or very dilute condition, the activity would be close to 1. Activity coefficient will be close to 1, which means activity equals concentration. That's under ideal. And of course, for some material that would have so-called positive deviation, which means your activity is actually higher than the concentration, or negative deviation the other way. That's what you learn, hopefully. And the mixing of ideal solution. We can just add the individual quantity together. Okay? And the regular solution, which is, okay, other than ideal, there will be some additional term. Phase diagram that we learned in phase diagram, right? The simplest one would be binary phase diagram, and we will look at one quickly in this class. And so-called phase. Last time we said we talked about phase. What does phase mean? A portion of a system that is uniform in its chemical and physical characteristics. Let me ask you this. When you go to the restaurant, the waiter gives you a cup of water but with some ice cube in it. How many phases within that cup? One or two? Two phase. One would be the liquid water phase. The other would be the solid water phase. Two phases. Make sense? Then let me tell you, you go to the restaurant, let's say the waiter gives you a wine or beer. Let's neglect the gas bubbles. The beer. Single phase, two phase. You look at it, it's pretty much the same, right? Transparent, pretty transparent, and uniform. You don't see one color here, one color over there, right? One density here, one density over there. Single phase, but it's so-called a multi-component because at least in the beer there is at least water, right? You're not drinking pure alcohol. There is at least some alcohol or ethanol in it. Otherwise, you just drink water. There's some sugar, some other stuff in there. Makes sense? But they all pretty much uniform. That's a concept of phase. Make sense? On the other hand, when you have oil and water together, you put them in one cup, what would happen? Based on your common sense, you have some oil, cooking oil, let's say, some water, you put them in one cup, what would happen? They would separate, the water would go towards the bottom because water typically compared with cooking oil is heavier, denser, while the cooking oil would be floating on the top. How many phases? Two phases. One is liquid one, we call it water phase. The other one is liquid two, we call it oily phase, right? The two have different chemistry, also have two different viscosity, different density, so two phase. Make sense? So that's phase diagram. What is a phase diagram? That hopefully you learned in more depth. Is about the diagram that tells you under what condition. We said equilibrium condition. Under equilibrium condition. That tells you what are the phases there, what are those phases, what are the composition for those phases. For simple binary, of course we can go to ternary. Binary is the simplest one. That's phase diagram. Gas reaction Ellingham diagram. If you studied it, good. If not, it's okay. That's not instrumental. Okay. And maybe some surface interfaces. And we will talk more about surface and interfaces, their energy aspect in this class. Okay.